Hey everyone, and welcome! I am so glad you're here for this explainer, where we're going to totally demystify one of the most essential pieces of modern tech, the battery. So this is the very first episode of the Lulito Series, coming to you from the E³ Nexus Lab, where we geek out on all things energy, environment, and electrochemical interfaces. Now, it's super important to know that for this explainer, we are sticking strictly to Chapter 1 of the book, Battery Technology Crash Course. We're building this house from the ground up, starting with a really solid foundation. Let's get into it. All right, so here's the game plan. We are going to pop the hood on that little black box we call a battery. We'll start with what a battery even is, at its core. Then we'll break it down into its essential parts. And finally, we'll get into the really key ideas that define how it performs: voltage, capacity, and the super important difference between energy and power. Okay, so when you think battery, you probably picture a AA, right? But what is that thing, fundamentally? What is actually going on inside?
Well, at its heart, every single battery is something called a galvanic cell. And the idea is actually pretty elegant. It's a device that's completely self-contained, and its whole job is to turn chemical energy directly into electrical energy. You can just think of it as its own tiny power plant running a controlled chemical reaction to power your stuff.
Now, you might be thinking, hold on, isn't that kind of what a fuel cell does? And that is a fantastic question. The key difference, the thing you gotta remember, is that a battery is a closed system. All the chemical fuel it's ever gonna have is sealed right inside that case. A fuel cell, on the other hand, that's an open system. It's more like an engine that'll just keep on running as long as you keep feeding it fuel from the outside. All right, so we know what a battery is, so let's take one apart, figuratively of course, and see the parts that make all this chemical magic actually happen. It's amazing, but every battery, whether it's in a tiny watch or a huge electric car, has these four critical parts. First, you've got the anode, that's the negative side. Then you've got the cathode, the positive side. In between them is the electrolyte, which is the special goop that lets charged atoms, or ions, travel back and forth. And finally, you have the separator, a really important barrier that just keeps the anode and cathode from touching. You do not want them to touch. So how does it all work together? Let's just follow an electron on its journey. When you use your phone, a reaction kicks off at the anode, and it releases electrons. Now, these electrons can't go through the middle of the battery, so they're forced to travel out through the external circuit, powering your device along the way. At the same time, to keep everything in balance, positive ions swim through the electrolyte and the separator. And then finally, the electrons finish their trip at the cathode, which welcomes them with open arms. That constant flow, that's your electricity. Okay, so we've got this flow of electrons, right? But what actually determines how hard they're being pushed through that circuit? Well, that brings us to voltage. And here's the crucial part. The voltage isn't just some random number. It's determined entirely by the chemistry inside. Scientists very carefully pick materials for the anode and cathode that have a big difference in what's called electrical potential. Think of it like a waterfall. The bigger the height difference, the more force the water has. It's the same idea here, just with electrons. So let me ask you a question. Think about your phone. As the battery percentage goes from 100% down to 50%, down to 10%, do you think the voltage is staying perfectly constant that entire time? The answer, it turns out, is nope, and chemistry tells us why. There's this principle, captured by the Nernst equation, that basically says as the chemicals inside the battery get used up, that potential difference we talked about, the height of the waterfall, it actually gets smaller. So in simple terms, as the fuel gets consumed, the push gets weaker. That's why a battery's voltage slowly drops as you discharge it. So we understand the push. That's the voltage. But how much stuff is there to be pushed in the first place? This brings us to the battery's capacity. Okay, first, let's talk about the ideal world, the perfect scenario. This is called theoretical specific energy. It's the absolute max amount of energy a battery could possibly hold if it were made of nothing but the pure active chemicals that do all the work. It's a number you calculate on paper with perfect chemistry. So for example, let's take a regular old lead-acid battery, like the one in most cars. Based purely on the chemistry of lead and lead dioxide, its theoretical specific energy is 167 watt-hours per kilogram. Not bad, right? But here's the kicker. The practical, real-world energy you can get out of that same battery is only around 33 watt-hours per kilogram. Wait, what? Where did more than 80% of that energy potential just disappear? Well, this huge gap between theory and reality is all about messy, real-world engineering. A real battery needs a plastic case, metal collectors, that separator, all of which add weight but zero energy. The electrolyte itself is pretty heavy. Plus, the reactions aren't 100% efficient. They lose some energy as heat, and often you can't even access all the chemical fuel you packed in there. It all adds up. Okay, this brings us to maybe the two most important concepts for judging a battery's performance. It is the classic trade-off: energy versus power. I absolutely love this analogy because it just makes everything click. Specific energy is the marathon runner. It tells you how much total fuel is in the tank. It's all about endurance, how long your device can run. Specific power, on the other hand, is the sprinter. It's not about how long you can run, but how fast you can go. It's about how quickly you can deliver that energy, the punch, the oomph, the acceleration. And of course, the dream, the absolute holy grail of battery design, is to have the best of both worlds, right? You want something that has the endurance of a marathon runner and the explosive speed of a sprinter. And there's this fantastic tool for visualizing this trade-off called a Ragone plot. It's basically a cheat sheet for batteries. It's super simple. The higher up you go on the chart, the more energy you have. That's your marathon runner. The further to the right you go, the more power you have. That's your sprinter. And you can see right away where different technologies shine. Lithium-ion batteries, great marathon runners. Nickel-cadmium, powerful sprinters. And fuel cells, they can run forever, but they're not winning any sprints. So think about how far we've come in just a few minutes. We started with the battery as this mysterious black box. And now we've pried it open, we get the 4 key parts and the fundamental rules: voltage, capacity, energy, and power that control everything it does. But you knew there was a but coming. This has all been Chapter 1, the basics, the ideal world. So the real question is, what happens when things get messy? What really limits a battery's performance in the real world, with things like temperature and how fast you use it, and just plain old aging? Well, we are going to dive into exactly that in our next explainer. So if you enjoyed breaking this all down with me, please don't forget to subscribe to the channel so you won't miss the next part of our Lulito series from the E³ Nexus Lab. Thanks so much for watching.